All right, so this will be the chapter 4 review, and there's a decent number of problems that are kind of calculator problems or do them in your head problems, and that's the first two problems that are staring at me on this page. I don't have a problem with you needing your calculator to do radicals, and there just really isn't work to show for these problems. So whether you do it in your head or do it by hand, there's not going to be a lot of partial credit for these problems. I suppose if I was doing 1A, I could say this is asking me what number squared is 121. If I wanted to get some partial credit and I made a mistake, the answer to this is just going to be 11, and it almost seems silly to write what I just wrote. I look at that and I know the square root of 121 is 11. I would expect you, if you didn't know it, to just hit your square root button, type 121, and it's going to tell you the answer is 11. Similarly, part B of this asks the question, what number cubed equals negative 64? And the answer is negative 4, because negative 4 to the third power is negative 4 times negative 4 times negative 4, and that's negative 64. Again, if you just write down the right answer, whether you used your calculator or knew the fact in your head, I won't know the difference. But if you write down an answer without any words, then I have no room to give you partial credit. So I guess this would be the saving grace for some partial credit. So this one, I'm hitting the shift in the square root key to get the cube root key, then the negative in the parentheses, and then 64, and then my answer is negative 4. It's not really x equal negative 4. There's not an x in this problem to say it's x equal negative 4. But if you wrote x equal negative 4, I'd hardly take any points off for that. C, if I was doing it by hand, I'd say this really means negative 1 times the square root of 49, which is negative 1 times 7. And the answer to part C is going to be negative 7. Equivalently, I could do that in my head without showing any work. I could do it on my calculator without showing any work by hitting the negative button in the parentheses, then the square root key, and then 49, and I'd get that negative 7 back. So for the first three problems on the review, I'd be content if you used your calculator, because they're just really calculator or know them in your head, no work problems. The next problems want me to make a graph, and I didn't bring graph paper today, but it's okay. Don't need graph paper. When we made graphs on the videos, I looked at the number inside the parentheses or under the radical, shoved it in the middle of my x column, and then I started doing 3 numbers smaller and 3 numbers bigger. If you checked my solutions manual would only show the numbers that you don't get errors for, but I kind of did a little extra in the video. And the nice thing about using this strategy for making a table, taking the number under the radical, changing its sign, putting in the middle of the x column, and doing 3 bigger and 3 smaller, it's consistent between square roots and cube roots. You don't have to vary between the two. And we used our calculator to get most of the tables. I'm going to use my calculator to get the table. I'm going to hit the mode button, and then option 7 for table. And this is square root. Remember, the x is on the right parentheses key. You hit the alpha button, the right parentheses, and then the minus by the equal sign, and then 4. So that looks enough like that function that I would believe my calculator's table. I'm going to start at 1. I'm going to end at 7. And always we step 1. In the first 3, next to 1, so I'm not looking at the first column, I'm looking at the second and the third column. Next to 1, 2, and 3, I get errors. So I'll write those down real quickly. Error, This is because 1, 2, and 3 aren't in the domain of the function. Keep going with this. Scroll down. Next to 4, I'm supposed to put 0. Next to 5, I'm supposed to put 1. Next to 6, it's 1 point. And it says round to 2 decimal places, so 4, 1. And 7 is 1.73. So I don't expect you to get all the y's by hand, but if you get the y's by hand, that's, you know, more power to you. You should have a similar table to me. You don't have to have the ones with the errors. It just helps me know that when I make a graph, it's, I don't know, it just helps me be more confident in my graph. So I'm going to just make a really crude graph here. It doesn't really need to be that good. On the x-axis, I'm going to put the numbers between 1 and 7 because my x column goes between 1 and 7. And on my y-axis, I really just need to go from up to 2 because my biggest y is 1.7. And so the first 3 points, they don't even get plotted because they don't have a y value that's plottable. The first point that's plottable is the point 40. If you want to and you write small and neat, you could write the point above or below or somewhere around each of the points, but you don't have to. So for 5, 1, I'm going to write it there. And then 6, 1.4. 1.4 is, you know, just under halfway up between 1 and 2. And 7, 1.7 is a little bit higher, but it's still beneath 2. And again, I could try to squeeze the writing in of the point, the x and the y coordinates of the points. I don't have to. So my graph is going to look something like this. I'm not going to be really picky about your graphs. Notice how my graph didn't even physically go through this point. I'll just make that point bigger to make that happen. So that's a reasonable graph. Your graph might look, you know, as long as it looks like this, I'm fine. It doesn't have to be exactly as steep as mine. It could go higher or go a little bit lower, just as long as you make a reasonable effort to plot the points and connect them. So I'm done with the table of values. I'm done with the sketch of graph. I used my calculator. Now I'm going to use the graph to find the domain and the range. And for the domain, all our square roots kind of had similar domains. This graph, in terms of left to right, starts at x equal to 4, and it goes off forever to the far right edge of the x-axis, which is at infinity. So for the domain of this, I'm going to say the domain goes from 4 to infinity. And then for the range, I read from the bottom of the graph to the top of the graph. And the bottom of the graph is at the point 40. The y coordinate at the bottom of the graph gets to be the first thing I write in my range. And its y coordinate is 0. And then I look to the top of the graph. And this graph, it'll blow off this page, and it'll keep going up forever and ever. Very slowly, it's going to work its way up to the top of the y-axis. It may, you know, might take a long time to even get to the top of this small y-axis that I have, but eventually the graph makes it up forever. It never starts going down, and so the end of the range is at infinity as well. So that's all there is to do for a nice square root graph. The next one's a cube root graph, and my table, at least the x column, is going to be the same because what's under the radical is the same. So I'm going to make an x column and a y column. I take the number -4 that's under the radical, change its sign, put it in the middle of my x column, and then put 5 numbers, 3 numbers smaller and 3 numbers bigger. And again, when I go to graph this, my graph is not going to be stellar. It's going to be just, you know, fair at best. But you don't have to have an awesome graph. Just as long as it looks reasonable, I'll be fine. So I set up my x column. I set up my x's on my graph. The far left edge of the x-axis is going to be important for the domain. The far right edge of the x-axis is going to be important for the range. In the videos, I think we mentioned that for all the cube roots that we're going to do, the domain is negative to positive infinity, and the range is also negative to positive infinity. Even without having the graph, for our class, there aren't any odd things that we do for cube graphs, and all of the cube graphs that we did, including any one that might appear on the test, we'll have that for the domain and range, and I'll show you that when I finish up my table, why that's the case. The domain is easy to see. The range is a little, less believable, but it's true. That's negative to positive infinity. So I'm hitting my mode button, selecting option 7 that says table, and then I hit shift and the square root key to get the cube root. So shift and square root gives me the cube root. Then the alpha button in the right parentheses gives me the x. Then I type in the minus by the equal sign in 4. And then my table starts at 1, ends at 7, step 1. And then the first x has a y of negative 1.44. The second x has a y of negative 1.26. The third point, the 3, has a y of negative 1. The 4 has a y of 0. The 5 has a y of 1. The 6 has a y of 1.26. And the 7 has a y of 1.44. So I like stealing the table from my table rather than doing all the points by hand. It saves a lot of time. I don't make as many errors when I steal a table from my calculator. Once you're done, and I think this is the last graph, once I'm done with my table, I need to get it in a nice mode. And for this test, if you hit the mode button and select the complex method option, you'll be better off for this test. So I'm done with my table. I'm going to hit the mode button and option 2 for complex, and that should take me through the rest of the test. So first point, 1, negative 1.44. That means I need to go down somewhere between negative 1 and 2, but not quite halfway. So I'm going to call that the point 1 and negative 1.44. Then 2, negative 1.26. That point is still beneath negative 1, but it's not quite as far down as that point, so I'm going to make it a little bit higher. And then 3 and negative 1, well, maybe it's about there. 4 and 0 is kind of easy for me to plot. And then for 5 and 1, I need to get a 1 on the y-axis. So this is about 5 and 1. 6 and 1.26, it's a little bit higher. 7 and 1.44, it's a little bit higher, but beneath the 2. And I'm just going to connect these points kind of the best I can. I could make the graph go all the way to the edge of the x-axis, and I could make the graph go all the way to the edge of the y-axis if I care to. Or I could just stop it where I did and put a little arrow to signify that it's going on forever. And it's hopefully clear that this graph eventually gets to the far left edge of the x-axis and the far right edge of the x-axis. That's why the domain is negative to positive infinity. It's not as clear, but eventually the graph gets to the bottom of the y-axis, and eventually, if you get out far enough, it goes to the top of the y-axis, and that's why I said the domain is negative to positive infinity. Again, for any cube root we're going to get on our test, that's going to be the domain and the range. We don't have any tricky domains and ranges for cube roots. We really don't have any tricky domains and ranges for square roots. The square root domain and range, most of the graphs, all the graphs we did had domains and ranges that kind of looked like that, or some number comma infinity. I can make variations of these problems that don't fit the mold, and you'd have to physically know how to, from your graph, to pick out the domain and range, but there's no tricks like that on the test. It's really straightforward. For 6, if you can divide an exponent by an index and not get a remainder, that's the best way to reduce a radical, and that's the case for 6a. 6a, I'm going to go 12 divided by 3 and drop the radical and get x to the 4th power. If I would have gotten a remainder, then that strategy wouldn't work. For part B, the negative means negative 1 times, and I have to separately do the square root of x to 8th and the square root of 64. For the square root of x to the 8th, I divide the exponent by 2, because in a square root, there's an implied index of 2. So I can think of this as negative 1 times x to the 8 over 2 power divided by the square root of 64, which I know to be 8, but I'll just make sure I'm not crazy. So the square root of 64 is 8. The radicals both drop. The negative 1, I didn't have to leave in the numerator. I could have left it like this. Negative 1 times x to the 8 over 2 divided by 8. That would both be acceptable for the negative 1. And now I'm going to simplify. In the numerator, I'm going to write negative 1 times x to the 4th over 8. This would be completely okay for a test answer. It's kind of odd to have the negative 1. You don't need the negative 1. This is probably a more common answer, just negative x to the 4th over 8. And this version of the answer, if I don't write the 1, it would be negative x to the 4th over 8. If I dropped the times and just put a negative, because negative 1 times something can be represented like that, that would also be okay. So I'm not going to be picky on the test. As long as you have a negative sign somewheres, either in the numerator or to the left of the fraction, an x to the 4th in the numerator and an 8 in the denominator, I'd be good with it. I guess you could actually even do this. You could say it's negative 1/8 x to the 4th. So if you just, for whatever reason, thought that was a nice way to write the answer, it's actually also correct. Anytime you have a fraction with only a monomial in the numerator, it has a letter. You could drag the letter and make it in front of the fraction or after the fraction. That's completely fine to do as well. So everything that I have circled, but probably not that, because that has the 8 over 2 that isn't reduced. So some variation of that would be fine. For C, I need to do the cube root of every piece. I need to do the cube root of negative 27. And I multiply that by the cube root of x to the 12th. And I multiply that by the cube root of y to the 6th. The cube root of negative 27, if I don't know it, I could do it on my calculator by going shift and square root for the cube root, and then negative 27. And that's going to give me a negative 3 for part of my answer. And then for the x, I'm going to divide its exponent by 3. And for the y, I'm going to divide its exponent by 3. And this strategy works best, and I only work it if I don't get a remainder. And so for an answer, for part C here of, I don't know what problem it is even, is negative 3x to the 4th times y squared. The next problems, you can majorly roll the dice and just use your calculator. A lot of students, for whatever reason, when they just use their calculator, enter things wrong. And when you enter things wrong, it makes it hard to give you partial credit. In fact, you won't get partial credit. So I'm going to show you how to do them by hand, and then I'll do them on my calculator. So for 27, this is going to be the cube root of 27 squared. The radical form of it's going to help me by hand. And now I'm going to do the cubed root of 27. The cube root of 27 I know to be 3. And then I'm going to square. And 3 squared is 3 times 3. My answer is going to be 9. If I wrote down a wrong answer and I showed this kind of work, I'm going to get partial credit. If you just ripped out your calculator and did 27 exponent fraction 2/3, and you did something bad on your calculator and didn't get this 9, then you're going to lose every bit of, won't get any partial credit. Again, B I could do on my calculator and take the risk of getting no partial credit if I make a mistake, or I could do it by hand. B by hand, because there's a negative exponent, I'm going to create a fraction to get that negative exponent positive. Then I'm going to change it to a cubed root. Then I'm going to do the cube root of 27 just like I did in part A. And then I'm going to do 3 to the 4th. And 3 to the 4th is 81. I don't need my calculator for that because I have it memorized. So the only answer that's acceptable for 27, or for part B of number 7, is 1 over 81. with my calculator, I would just go 27 exponent fraction negative 4 over 3, and it's going to give me the 1 over 81 that I came up with. 64, or C by hand, if you have a negative exponent outside a fraction, you take the reciprocal of the fraction and make the exponent positive. And now, what's in the parentheses has a denominator of 1, so it doesn't really need to be written as a fraction. By hand, I can say this is 64 to the 3/2 power. Then I can write it as a radical. It's going to be the second root, which is the square root of 64 cubed. And then, by hand, first I'm going to square root the 64. And the square root of 64 is 8. And then I'm going to cube the 8. And I believe that's 512. I'm going to check it on my calculator to make sure I wasn't doing funky bad math in my head. 8 cubed is 8 times 8 times 8, and I'm pretty sure that's 512. If I'm doing it by hand, I'm just going to enter the entire first problem how it was given to me. So by hand, I'd go parentheses, fraction, 1 over 64, get out of the denominator, parentheses, exponent key, fraction negative 3 over 2. And that more or less looks like what I have written, other than the fractions written vertically as opposed to horizontally. I write them horizontally so they don't take as much room. And I get 512, just like I suspected. So for these three parts, A, B, and C of number 7, when they come on the test, the only chance you have at partial credit is to show what I showed here. If you just write an answer down and use your calculator, is not the most important skill to me. I'll slide unless you have a few free points. But if you just use your calculator and don't get exactly the right answer, then you won't get a single point. For 8A, because there isn't any letters, I could do it on my calculator. I'll do it by hand just because it's not that hard, and that's the way to guarantee yourself the partial credit. For 8A, because the 3's are being multiplied, that's considered multiplying terms with the same base. And when you multiply terms with the same base, you add the exponents. And the exponents add together to become a 6/3, because 1/3 plus 5/3, you add the 1 and 5 and get 6. And the 3 stays when you're adding the fractions. And then that gives me 3 squared, because 6 over 3 is 2. And for an answer to number 8, I'm just going to write the number 9. And then by my calculator, because it doesn't have any letters, 3 exponent fraction 1 over 3, get out of the exponent, and then times 3 exponent fraction 5 over 3. Again, that looks enough like the problem that I believe the answer is going to be correct, and I get that 9 again. So I'm good with that one. Probably on the test I'll be evil and give you letters there so your calculator won't work. For part B of 8, I need to make the negative exponent positive, and I'm going to create a fraction. Well, I'm going to actually, I already have a fraction, but I'm going to tuck the x to the negative 1/2 down into the denominator of the fraction, because to make a negative exponent in a fraction that only has multiplying, you just move the negative exponent piece from one side of the fraction to another. The 4 does not have a negative exponent. In order for the 4 to go down to the denominator, the numerator would have had to have been 4x to the negative 1/2. If this was the numerator, then the 4 would also go to the denominator. So if this were, I don't know if it's were or was, the numerator, then the 4 would go down. But in this case, the negative 1/2 only applies to the x. The x is the only thing that goes down from the numerator. The 4 stays up top. Just like the last problem, I have a multiplication with fractional exponents. I'm going to add the exponents. 5/2 plus 1/2 is 6/2, and 6 over 2 reduces to 3. So for my answer, I'm going to write 4 over x cubed. 8c, I have to raise everything to the 4th power. I could simplify the inside of the parentheses first, which that's what we're doing in the video, so I'll do that. The first thing I want to do is get the 2y's down to 1y. And for the second y, that's going to involve getting a new denominator. And the exponent of 1/2, I'm going to get it to have an exponent of 4, or of a denominator of 4, by multiplying this exponent by 2 over 2. I get it to 2 over 4. Now the 2y's can be added or multiplied, and you multiply them by adding their exponents. And that's going to give me 2y to the 5/4 power. And now I'm going to raise everything to the 4th power. So I'm going to raise the 2 to the 4th power, and for the y, I raise it to the 4th power by multiplying its exponent by 4. I can do both of these in my head, but let me do them on my calculator. The 2 to the 4th power, 2 to the 4th power is 16. So that's part of my answer. And the exponent on the y is 5/4 times 4. Got to be out of the denominator when you do that. So it's 5/4 times 4. And that's equal to 5. Because anytime you're multiplying a fraction by an integer, you could cancel the denominator with that integer. And so my answer is going to be 16y to the 5th. That's because this 2 to the 4th is equal to 16. And for the y's, you can cancel these 4's, and you're left with y to the 5th. Nine wants me to write radical notation. This is supposed to be 3x to the 1/2 power. I'll make it look more like that. That doesn't look so much like 1/2 power, but it's what it's supposed to be. So anytime I see 1/2 power, I know I'm going to get a square root. Anytime I see a fraction exponent, I know I can write it with a radical. So both 9a and 9b can be written with a radical. The trick is knowing what to put under the radical and what, if anything, goes in front of the radical. And that's why I have a 9a and a 9b, because they illustrate when everything goes under the radical and when the letter just goes under the radical. In 9a, because both the 3 and the x are in the parentheses, they both go under the radical because they're both being square rooted. 1/2 power is same as square rooting. In part B, the 3 is not being square rooted, it's not being raised to the 1/2 power. Only the x is being raised to the 1/2 power. So in part B, only the x goes under. So the big difference is between A and B is in A, because the 3 is in a parentheses, it belongs under the radical. In B, because the 3 is not in a parentheses, it goes in front of the radical. So we'll say a number inside a parentheses that has a fraction exponent goes under the radical. But if the number is not in a parentheses and the letter has a fraction exponent, then only the letter goes under the radical. So always when I put this kind of question on the test, I usually only do one of the two, and consistently a lot of students miss them. So we really want to make sure you don't fall into the trap of putting the number where it doesn't belong. So it's not terribly hard, but it's tricky enough that students mess it up. So the difference between 9a and 9b in terms of how we're dealing with the coefficient is if the coefficient is in a parentheses, it belongs under the radical. If the coefficient's not in a parentheses, it goes in front of the radical. both of the answers that I have written down here, although they're correct, they're probably not the best answers because they both have exponents of 1 written, and we almost never write an exponent of 1. So I'm going to rewrite the problem without the exponent 1. And in part A, I'm going to dump off the parentheses because the parentheses aren't so necessary either when I don't have an exponent outside them. So for a better answer to number 9, A, I'm going to write the square root of 3x. And notice I didn't even write the index of 2 because the index of 2 is assumed. So this is probably a better answer. I should probably write the word answer next to it, but I'll live without it right now. And for part B, a better or best answer would just be 3 times the square root of x. You don't need to write the index of 2. That's assumed in a square root problem. You don't need to write the exponent of 1 almost ever. Ten's going backwards. And to go backwards, it's probably easiest to give everything under the radical a fraction exponent. So if something is under the radical and I'm asked to write it with fraction or rational exponent, so if I'm asked to write with a fraction exponent with a I will write everything under the radical with a fraction exponent. It's not the only way to do it, but it's a really safe way to do it. For part A, I have to think of this as the cube root of 2 to the first x to the first, and just like I did a few problems back, I'm going to divide the exponents by the index. So a really nice answer for 10A, should I say, would be 2 to the 1/3 x to the 1/3. It turns out it would also be okay. So if you worked ahead and you got this for an answer, that's also okay because they both have fraction exponents. This is equivalent because I raised both of them to the 1/3 power. In part B, I have to remember that only the x is going to get a fraction exponent because the 2 is not under the radical. It doesn't get a fraction exponent. The x under the radical had an implied exponent of 1. I'm just going to divide the exponent by the index to get it in radical form. So a big difference between 10A and 10B is only the things under the radical get the fraction exponent. The number in part B is not under the radical. It doesn't get a fraction exponent. For 11A, I'm going to multiply the 3 and the 27. I'm going to multiply the x and the x. Since everything's under the radical, they're going to stay under the radical. 3 times 27 is 81, and x times x is x squared. Then I'm going to do the square root of 81. I'll use my calculator for that. And I'm going to do the square root of x squared. And to do the square root of x squared, for a square root, I divide the exponent by 2. The square root of 81, I guess I just know it's 9. And for the x, I'll go x to the 2 divided by 2 power and get x to the first power. So my answer to 11A is just going to be a 9x. For part B, I'm going to multiply the a's by adding their exponents. I'm going to multiply the b's by adding their exponents. And the first b that didn't have an exponent written has an implied exponent of 1. So this, when I simplify the 2a's to 1a, I'm going to get a to the 12th. When I simplify the 2b's to 1b, I get b to the 12th. Now I'm going to drop the radical, and in order to drop a radical, everything under the radical needs to have its exponent divided by the index. The index is 4, and when I divide, I'm going to get an answer of a cubed and b cubed. 50, my calculator, or 12, my calculator will do. Square root of 50 is 5 square root of 2. And again, this is one of those problems where I'd live with you just pressing buttons, but I'll probably make it so your calculator won't get you the whole way. I'll throw some letters in there. If I wanted to do this by hand, because that's the only way you could ever get partial credit for a wrong answer, the 50 I'm going to say is 5 times 10. 10 I'm going to say is 2 times 5. So 50 is 2 times 5 times 5. Remember, we could do the factor trees on our calculator. On my calculator, I'd go 50 equals, and then shift and factor. Really? It made it degrees in minutes. I'll be darned. Oh. Actually, I was helping a student with calculus before, and our trig, it's not working on this. I must have to be in a different mode. Oh, it doesn't do factoring in complex mode. Let me go mode 1, and now go 50 equals shift factor, and there's my 2 times 5 times 5, which is 2 times 5 squared. And every time you get a pair in a square root, you get one of these out, and single stay in or under. So that's why I get a 5 out and a 2 under. For part B, it's a cube root. My calculator doesn't do cube roots well, so I'm going to do a prime factoring for 40. I have to be in mode 1 for prime factoring to work. And now I'm going to go 40, and then shift, and then factor. Whoops, I had to go 40 equals. Sorry, I needed to get the 40 down in the bottom right-hand corner. So I did 40 and equals, and then shift and factor. And that tells me it's 2 cubed times 5. So 40 is equal to 2 times 2 times 2 times 5. And in a cube root, every time you get 3 of a kind, you get 1 out front. And anything less than a 3 of a kind stays under. So in this problem, I'm going to get 2 times the cube root of 5. For C, I need to do everything separately. So I need to do 27x, y to the 6th, and z to the 7th. Reduce each of them. First thing I'll deal with is the 27 by going 27 equals shift factor. 27 is 3 times 3 times 3. So for 27, I get a 3 out and a 3 under. So as I go to write my answer, I'm going to put a 3 under the radical and a 3 in front of the radical. I could have just did square root of 27 on my calculator, and it would have told me that it was 3 and 3. The x is not a pair, and you need pairs to get 1 out, so I'm going to just leave an x under. The y, you could divide the exponent by 2, or you could start making pairs. I write 6 y's. That leaves me with 3 pairs of y's, so I'm going to get 3 out, and there isn't any singles left over, so there's none for under my radical. So in my answer, I'm going to have a y cubed out. For the z to the 7th, I'm going to write 6z's, 7z's should I say, and when I do that, I get 3 pairs, so I get 3 z's out and 1 left over for under. So the z's are going to have a z cubed out and a z under. You can definitely do these in your head if you're, can do that kind of stuff in your head. And again, I don't have an issue with you doing things in your head, but it really slows down your partial credit if you make a mistake. 13, I'm subtracting, and there's the same numbers or same letters under the radical. So you just, part A, you just subtract the 6 and the 4 and get 2. And when you're adding or subtracting, the square root part doesn't change. For B, The square root of 25 is 5, so I can replace it with 5. The square root of 49 is 7. I can replace it with 7. Then I could just add 5 and 7 and get an answer of 12. C I could do on my calculator, and I'll show you how to do it by hand. On my calculator, it's 5 square root of 18 plus 3 square root of 50, and I get 30 square root of 2 for my answer. By hand, I want to reduce the 18 and the 50. So I'm going to go 18 equals shift factor. 18, its factoring is 2 times 3 times 3. I'll do the same for 50. 50 equals shift factor. 50 is 2 times 5 times 5. So for the first radical, it has a 5 out front already, and I'm going to bring a 3 out because I have a pair of 3's, and I'm going to leave a 2 under. For the second radical, it already has a 3 out front. I'm going to leave it there. I'm going to bring a 5 out front from the pair of 5's in its prime factor, and I'm going to leave a 2 under from the single 2. So this gives me 5 times 3 square root of 2 for the first piece, the 5 that was there, the 3 that came from a pair, and then 3 times 5 square root of 2, the 3 that was there, the 5 from the pair. This gives me 15 square root of 2 plus 15 square root of 2, and that takes me to the 30 square root of 2 that I know is the right answer. For A, I can multiply them easy enough. The square root of 3 times the square root of 6 is the square root of 18. And then I could just, well, I could do this whole thing on my calculator. Square root of 3 and square root of 6 next to each other. See, it's so hard to get this. The answer is going to be 3 square root of 2. By hand, I'd multiply the 3 and the 6. Then I do a prime factoring for the 18. 18 is 2 times 3 times 3. That tells me I get a 3 out from the pair of 3's and a 2 under from the single 2. For B, I'm going to multiply the 4's together. I'm going to multiply the x's together, and I'm going to multiply the y's together. The 4's just multiply to be 16. The x's, I need to add their exponents. 1 and 2 gives me an x cubed. For the y's, I need to add their exponents. 1 and 5 gives me a y to the 6th. Each I can reduce by prime factoring, or the x's and the y's, I could actually divide their exponents. 16, the prime factoring is 2 times 2 times 2 times 2. I did it in my head, but you can do it on your calculator. And so in my answer, I'm going to have a 2 outside the radical, and then the cube root symbol is going to stay, and I'm going to get a 2 under the cube root. For the x cubed, when I write 3 x's, I get 1 x in front of the radical and nothing left over for under the radical. And for the y to the 6th, when I write 6 y's down, I get 2 y's out and nothing left over for a y under. So my answer should be 2xy squared in front of the radical and a cube root of 2 under my radical. Still feels pretty thick, and I think this review is quite so long. For part C, I'm going to multiply the 8 and the negative 2a that were outside the radical and leave them outside the radical. And then I'm going to multiply the ab and the b that were under the radicals. The 8 and the negative 2a in front of the radical, you multiply those and you get negative 16a. Under the radical, the a's got to stay in a, and then the b's, you add the exponent and get a b squared. The only thing I have to worry about is simplifying under the radical. Under the radical, there's a single a and a pair of b's. The pair of b's, you're going to get a b outside the radical and not a b under the radical because there's nothing left over. And the single a, because there's not a pair, it's going to stay under the radical. So from this line to get to an answer, the a is going to stay under the radical. There's not going to be a b under the radical. There's going to be a b in front of the radical, and I'll put it next to the a. So my best guess for an answer to this is going to be negative 16 ab in front, and then under just a single a. D, my calculator will do. So D is 2 square root of 3 times 4 square root of 3 minus square root of 2. And I get error. I don't know what I did wrong. I have the parentheses in the wrong place. Needed to get the parentheses outside that radical. And my answer is going to be 24 minus 2 square root of 6, if you can actually read that. To get that by hand, I'm going to multiply 2 square root of 3 times 4 square root of 3, and I'm going to multiply 2 square root of 3 times negative square root of 2. For the first one, I multiply the 2 and the 4 and get an 8 in front of my radical. I multiply the 3 and the 3 and get a 3 under my radical. For the next one, I think of this as 2 square root of 3 times negative 1 square root of 2. And I multiply the 2 and the negative 1 and get a negative 2 in front of the radical. And then the 3 and the 2 give me a 6 under the radical. 9, I know its square root is 3, so that's going to give me 8 times 3, which is 24. And then the second piece isn't going to reduce because the prime factoring for 6 doesn't have any pairs in it. And so my calculator's answer and my by hand answer are going to be the same, even in the same order. Sometimes my calculator answer gets a different order than my by hand answer. E is foiling. I'll do it on my calculator real quickly first. So, if we can see that, so 5 square root of 3, oops, clear, 5 square root of 3 plus 6 square root of 2 times 4 square root of 3 minus square root of 2, and my answer is 48 plus 19 square root of 6. Shouldn't be that hard to get there by hand. It's just a simple foiling problem. My firsts are 5 square root of 3 times 4 square root of 3, and that's 20 square root of 9 for the firsts. My outers are 5 square root of 3 times minus, I'll say 1 square root of 2, and that gives me 5 times minus 1 is minus 5, 3 times 2 is 6. My inners are 6 square root of 2 times 4 square root of 3. I multiply the 6 and the 4 and get a positive 24. I multiply the 2 and the 3 and get a 6 under my radical. And then the last 6 square root of 2 times negative 1 square root of 2. 6 times negative 1 is negative 6 in front of the radical. 2 times 2 is 4 under the radical. The outers and the inners, they have the same numbers under the radical, and I subtract the 5 from the 24, and this gives me a positive 19 square root of 6. The first can be written as 20 times 3 because the square root of 9 is 3. The last can be written as 6 times 2 because the square root of 4 is 2. So this is going to be 60 plus 19 square root of 6 minus 12, which I can think of as 60 minus 12 plus 19 square root of 6. The 60 minus 12 gives me the 48 for the answer, and that 19 square root of 6 was already there for me. Hey, finally to the I problems. I'm going to get my calculator back in complex mode. I won't factor in complex mode, but certainly do this. So mode 2, and now square root negative 50. The answer is going to be 5 square root of 2 times I. The I is not under the radical, it's after the radical. By hand, I'd have to get a prime by hand, I get an I when I have a negative under a square root. And then the prime factoring for 50, 50 is 5 times 10, 10 is 5 times 2. The prime factoring for 50 is 2 times 5 times 5, which gives me a 5 outside the radical and a 2 under the radical. So I know anytime I have a negative under the square root, I need complex mode on my calculator. By hand, I can make that negative into a positive I by putting it in front of my radical or after my radical, and then I could prime factor to get the radical reduced if I want. 20 square root of negative 9 times square root of negative 4, didn't write that right, times square root of negative 4. The answer is supposed to be negative 6. By hand, the square root of negative 9 is 3i. The square root of negative 4 is 2i. Then I'm going to multiply the 3 and the 2 and the I and the I. 3 times 2 is 6. I times I is I squared. And this gives me 6 times minus 1, which is minus 6. 21 square root of negative 2 times the square root of negative 18 gives me negative 6 again. I'll be darned. To get there by hand, I go, this is the square root of 2 times I times the square root of 18 times I, and then I'm going to multiply the square root of 2 and the square root of 18, and I'm going to multiply the I and the I. The square root of 2 times the square root of 18 is the square root of 36. I times I is I squared. Square root of 36 is 6. I squared is negative 1, so that this line reduces to 6 times negative 1, which is my negative 6. 22, 6 minus 5i minus parentheses 4 minus 3i is 2 minus 2i. To get there by hand, first parentheses I just drop. Second parentheses I write the opposite when I drop it. The opposite of positive 4 is negative 4. The opposite of negative 3i is positive 3i. Then I have to go 6 minus 4, which is going to give me the 2. And minus 5i plus 3i is going to give me the minus 2i. 23, 4 minus 3i parentheses squared equals to 7 minus 24i for an answer. By hand, I have to make this a FOIL problem. It's 4 minus 3i times 4 minus 3i. Firsts are 16. Outers are minus 12i. Inners are another minus 12i, and the lasts are minus 3i times minus 3i. That's a positive 9i squared. The outers and the inners don't cancel because they have the same signs. I add the 12s and keep them negative. The outers and the inners give me the minus 24i part of the answer. The firsts, 16, and the lasts, plus 9i squared, are going to give me the 7. The 9i squared can be written as 9 times negative 1, so I can think of this as 6 minus 24i plus a negative 9, or I can think of it as 16 minus 24i minus 9, and the 16 minus 9 part is going to give me the 7 that my calculator gave me. Okay, I don't want a plus or minus sign here, I just want a plus here. Let me change this to 12 plus the square root of negative 20 over 2 times 4. Sorry about that little hiccup there. That's something that's more appropriate for Chapter 5 and not really what we did at all. So as I do this problem, we entered it on our calculator, we also do it by hand. I'll do both. My calculator, I'd go fraction 12 plus the square root of negative 20 over 2 times 4, and my calculator is going to give me a 2 fraction answer. I'm okay with that. So my calculator answer is going to be 3/2 plus the square root of 5 over 4 times I. 1 by hand, my 2 fraction answer by hand is going to have the I in the numerator. It's going to be 3/2 plus the square root of 5 times I over 4. And my 1 fraction answer is going to have a 4 in the denominator. Let me do this by hand. The first thing I'm going to do is reduce the square root of -20. And the square root of -20 reduces to 2 times the square root of 5i. So by hand, I'm going to say this is 12 plus 2 times the square root of 5i. And then I'm going to write an 8 in the denominator. And then this, and this are all reducible by 2. So to get a 1 fraction answer, I'll go 12 divided by 2 is 6, 2 divided by 2 is 1, 8 divided by 2 is 4. That's the 4 I knew I was going to get, because usually by hand you get the denominator that's the bigger of the two. And I'm going to write 6 plus square root of 5i, 5, and then the I is after, something like this. 6 plus the square root of 5 times I over 4. That's the answer I would come up with if I was doing it by hand. To get this by hand, you take this and make this 12 over 8 plus 2 square root of 5i over 8, and I wrote a 6. 12 over 8 you reduce by 4. 12 divided by 4 is 3. 8 divided by 4 is 2. And in this fraction you go 2 divided by 2 is 1, but I don't need to write the 1 because there's already stuff in the numerator. 8 divided by 2 is 4. That will take you to that answer. Any one of these 3 answers is fine by me. I don't have a strong tie to any of the answers, so whichever one you come up with is fine. 25, I need to cube both sides to get rid of the cube root, because cubing gets rid of a cube root. So on the left side, the cubing cancels out the cube root. It leaves me what's under the cube root. And on the right side, 3 cubed is 27. So my answer to 25 is going to be 27. For 26, I'm going to square both sides to get rid of the square root. So I'm going to go square and square. On the left side, when you square a square root, you get the stuff under the square root, and it doesn't change what's under the square root. On the right side, 8 squared is 64. Now I need to get the numbers on one side, the letters on another. I don't need to factor because there's not a square. So this is going to give me minus 5x equals to 62. And then I'm going to divide by -5. And I'm going to get x equals 62 over -5. It seems bizarre to have the negative written in the denominator, although it would be okay if you wrote 62 over -5, but I like that better for an answer. I'm not checking, but I checked a lot on the videos, and you're welcome to check your work. 27, I'm going to write it as a radical. As a radical, it's going to be the second root of x minus 3 to the first equals to 2. I have some things that aren't necessary. I don't need to write a 2. It's assumed in a square root. I never need an exponent of 1. So I'm going to rewrite this problem as just the square root of x minus 3 equals to 2 by just dropping the unnecessary bits. And then I'm going to square. On the left side, squaring leaves me what's under the square root. In this case, it's an x minus 3. On the right side, 2 squared is 4. And now I'm going to add 3 to both sides and get my answer of x equal to 7. Again, you can check these, and you probably should check these. If you need help checking these, come visit me and I'll show you how to do it. 28's tricky. You have to isolate the square root first. I'm going to isolate the square root by first minusing 4 from both sides. That's going to give me 2 times the square root of 3x equals to 8. And then I'm going to divide both sides by 2. Doing those 2 steps are going to make it so it's going to be easier to square both sides and give me an answer that checks. So I isolated the square root by minusing 4 and dividing by 2, and now I'm going to square both sides. On the left side, squaring cancels out the square root. It leaves you the stuff that's under the square root but doesn't change it. On the right side, 4 squared is 4 times 4, which is 16. And then I just divide both sides by 3. And get x equals 16 over 3. Last problem is the evil one. It's the one where if you don't check, you could write down an answer that doesn't work. I think it's the last problem. Yes, it is. So on the last problem, I'm going to square both sides. The left side's easy. The squaring just cancels out what's under, cancels out the square root, leaves me what's under the square root, doesn't change what's under the square root. On the right side, I'm going to FOIL, and firsts are going to be x times x, which is x squared. Outers are x times minus 3, which is minus 3x. Inners are minus 3 times x, which is minus 3x. Lasts are minus 3 times minus 3, which is plus 9. So this gives me 2x minus 3 on the left side. When I combine the outers and the inners, I get x squared minus 6x plus 9. Because there's a square, I need to set it equal to 0. I'm going to minus 2x and plus 3 to get it set equal to 0. This is going to give me 0 on the left side and x squared minus 8x plus 12 on the right side. I can factor this. It's a double negative. My template from back a few chapters ago told me this would be a double negative. And for the double negative factors of 12, I have -1 and -12, -2 and -6, or -3 and -4 to choose from. The only one that gives me the 8 is the -2 and -6. Now I'm going to go x minus 2 equal to 0 and get x equal to 2, x minus 6 equal to 0 and get x equal to 6. If you don't check, you're probably going to write down a wrong answer because one of these doesn't check. So I need to go to the original problem, which was the square root of 2x minus 3 equals x minus 3, and plug in 2 is the square root of 2 times 2 minus 3 equal to 2 minus 3, and then do the same thing with the 6 is the square root of 2 times 6 minus 3 equal to 6 minus 3. Turns out that the 6 works, the 2 doesn't. So for the 2, I'm going to do the left side, and the left side wants me to do square root of 2 times 2 minus 3. The left side gives me positive 1. And the right side, 2 minus 3, gives me negative 1. That's called an extraneous solution. You shouldn't include 2 in your answer because it doesn't check. For the other side, the square root of 2 times 6 minus 3, see that, equals 3. And on the right side, 6 minus 3 equals 3. So the only answer I should write down is the one that checks, and that's x equal to 6. If this was a test question, and if you wrote 6 comma 2, you're going to lose a point or two because 2 isn't a solution because it doesn't check. So that's the entire review. There could never be anything, or should never ever be anything on a test that I give that isn't just like something on the review. So if you have this review perfected, then you can come into the test with confidence. Of course, make sure you turn in your homework if you want to use a note card, and make sure you visit me if there's something you just don't understand, because I want you to understand it before you take the test rather than learning it after you make the mistake, or any mistake.